Good morning, everybody. Welcome to another wonderful morning of Chem 1105 with your host, me, Dr. White. Now, one thing I do want to mention right now, for those of you who haven't gotten the code yet, access code for Beyond Lab Z, tonight in my office hours, stop by, or if you can, Friday after lecture, stay around and I'll help you do the lab and I'll open it up. I'll generate the data. You got to write it down and that way you can hand it in. So if you don't have the access code yet for Beyond Lab Z, also email me because if enough people don't have it, I think I'm going to complain to someone. This is the third semester in a row that the bookstore has just been bad. I'll leave it at that. And it's for those who celebrate. It's the second day of Rosh Hashanah. Hopefully you're having a healthy and happy new year. Lashana Tov. So far, I am. Also, if you haven't gotten your vaccinations yet, get them and wear your mask. It's getting interestingly dangerous out there. Interesting way to put it. All right, let's get to work. First of all, don't forget, yesterday you should have handed in the lab unless you don't have your access code. If you didn't, make sure you do it today because you don't want to lose 10 points. I don't want to take them away from you either. All right, let's get to work. Now, yesterday, I started talking about polyatomic, yesterday. Boy, having Monday off makes messes up my brain good. All right, talked about polyatomic ions, and those are ions that atoms acquire an electrical charge, which is shared among the group of atoms. And I didn't go through nomenclature, naming. Nomenclature, I'll use that term, is a fancy way for naming. There are other things I'd rather go through in this class for you people, because naming you can look up on the internet. All right, now, here's some key. I have at the bottom, know these names, really be familiar how to use them. NO3 minus nitrate, NO2 minus nitrite. And I'm not asking in the past, I asked students to memorize these names. I've changed that. And SO4 minus 2 or 2 minus is sulfate. HCO3 minus 1 is bicarbonate. And later on, near the end of the semester, we'll talk a lot about the hydronium and the hydroxide ions. But as I did on yesterday, I want to say Monday, but actually yesterday, I talked about writing the empirical formula for different ions. I tell you, I was always the first one down in the spelling bee. Let's try that one again. And sometime in your future, you see this on a piece of paper you printed out or on a screen. You're reading from 3 points each. Write the empirical formula for. Remember, and this is your turn. I'm going to start out with, you get to go first. Write the empirical formula for a molecule with sodium plus cations and bicarbonate anions. Remember, all molecules have all molecules, you should remember, have a net zero charge. And now go ahead, write the empirical formula for that. And for those of you with your web camera on, thank you. For those of you who don't, could you turn it on, please, to make Dr. White me happy, which is a good thing in life, especially if you're me. Also good for my students. All right, let's do this. If we look at sodium, it has a +1 charge. Bicarbonate has a -1 charge. All charges of the molecule have to end up to 0. I put the line in there so you know I'm not writing the letter O. And in this case, it does. So what that tells us is the molecule has 1 sodium and 1 bicarbonate. And that would be the empirical formula. Now, how many of you are familiar with the little red can or yellow can of stuff called baking powder in your kitchen? Or if you live with someone else, in their kitchen. And that's this compound, sodium bicarbonate, also known as baking powder. And the main brand is Calmet, which is in a little red can. I should have brought mine. Now, I haven't seen it in a while, but there's a company in Indiana that makes baking powder. It's in a yellow can and it has the weirdest name, Gabbler Girl. How it got that name, but one of these days I'll look it up on the internet, but it's a weird name, Gabbler Girl. All right. Oh, these are fun. Let's do another one. Here's another one for you to have fun with. And we got almost a full house today. Thank you. I guess everybody showed up. Will we have sitting room only? Because nobody's standing. Uh-oh, it's awful humor Wednesday. Sorry. All right, let's do this. If we have calcium +2 and nitrite -1, it has to add up to 0. It doesn't. Listen carefully. Common mistake students do is, oh, I can change this to -2. You can't. You can change how many there are. And if this is a +2, 2 times -1 is a -2. Now it adds up to 0. So I have 1 calcium. Oops, don't need the plus charge. And because I have 2 polyatomic ions here, I need a bracket, NO2, and then subscript here, I put a 2 there, and that tells me there are 2 of these, 1 of these, and that's calcium nitrate. Nitrite, I always get those mixed up. Now, how many of you have heard you need to get all your calcium so you have strong bones and you don't get certain diseases when you get old, like osteoporosis, which if you've ever met anybody who's had that, it's not something you want to get. And what do they tell you to take? Make sure you get enough calcium in your diet. Now, calcium is an element, and it's just as hard as the gold of my ring. And you're not going to want to chew on that because you'll break all your teeth. That's not a good thing. And I don't think your stomach can digest it. So what do they mean by taking calcium for strong bones? Not the metal, the ion. You take calcium plus 2 ions, and that makes strong bones. How? Well, I'm an organic chemist, not a medical doctor. But let me show you something. Thumbs up, people. Do you see calcium citrate on your screen? Thank you. This is the molecule calcium citrate. This is a polyatomic ion called the citrate ion. I'll talk about it more when we get into it. And it's a complex molecule, but it has calcium plus 2 cations, and the citrate is a -3, each one of these minus, and this is 3 of these, 2 of those. Now, what this does is it provides your body with the calcium plus 2 cations, and that helps make strong bones. So next time you see something you're going to buy and it says fortified with calcium on the label, it's not calcium metal, it's calcium plus 2 cations. And if you happen to be with a friend, neighbor, loved one, and you're in the supermarket and you see that, you can point it out to them now that that has calcium plus 2 cations. No, don't do that. People hate to hear chemistry in supermarkets. Also in big box stores like Home Depot, trust me, I've done that, and no, I shouldn't have done that. And also at dinner, lunch, or breakfast, don't talk chemistry then. They don't want to hear it. Sad but true. All right. And I've talked about how to write the formulas. We just did that. Remember, all ionically, actually all molecules, not just ionically bonded molecules, have a net zero charge. And you follow the way we've already done balance for polyatomic, like the simple ones. Uh-oh. Uh-oh. We finished part 1 of chapter 4. So you know what that means? It means it's time for part 2, chapter 4. Now, in part 1, we talked about ionic compounds and ionic chemical bonds. Remember, there are 2 types of chemical bonds, ionic bond and a covalent bond. And now it's time to talk about covalent bonds. And hopefully everybody sees part 2 on your screen. If not, yell out at me. And in part 2, we'll be talking about covalent bonds. Now, this slide is something from your book. They're most of the time, not always, between similar or identical atoms. Most important thing, they involve sharing pairs of electrons. Remember, pair means 2. And in some books, I never understand, I sort of do, but it's funky. Basic structural unit is a molecule. Well, they all are molecules. All right. Time for Dr. White to be subtle. Now, what is a covalent bond? A covalent bond is the sharing between two atoms of pairs of electrons, a chemical bond between two atoms resulting from the sharing of pairs of electrons. So between two atoms, when you share pairs, remember pairs are two, of electrons, you have a covalent chemical bond. Hint, you should know this. Now, when we talk about covalent bonds, a good way to show this is Lewis structures. Now, Lewis structures for elements, you put one dot on each side before you double up. In molecules, you don't use that rule, and I'll show you. Now, let's look at the simplest molecule I can think of, and that's hydrogen gas. Hydrogen gas is H2. That means two hydrogen atoms bound together. Now, each hydrogen has one electron and also one valence electron. And it exists as I have here as H2. Now, here's this Lewis structure. This hydrogen has one electron. This one has one electron. I bet you don't know atoms can talk to each other. They can't, but it sounds nice. This atom, hydrogen, says to that one, I've got an electron, you've got an electron, let's share. And they do. And this is the Lewis structure for hydrogen gas, H2, which is a molecule. And notice the two electrons being shared, that's a covalent. Covalent chemical bond. And hydrogen gas is an important chemical used industrially throughout the world. And I've used it industrially, both in a lab and in a chemical plant. How many of you, and I'll teach this later in the semester, both since we're talking about hydrogen, how many of you have heard of hydrogenated fats and oils, which are not good for you, but that helps companies sell things like margarine and other things. You use hydrogen gas to make that. And I've worked with it. It's quite dangerous because hydrogen is very flammable. And if you don't work properly with it, it will blow up. And if it blows up in a chemical plant, you're dead. Good news, never happened to me, as you can tell. But you take it very seriously. And later on, when we get into organic, I'll talk more about that. And it's important, this is why I didn't ask you to learn past magnesium, that's our secret, about electron configuration, because the valence electrons are the electrons used in a covalent bond. And therefore, those are important. Now, I talked about the octet rule, in which molecules can lose, gain, that happens for ionic compounds, but they can share electrons to achieve an octet. Octet means you have 8 valence electrons. And here I show for shell number 2, and I could have put instead of the big 2 in front of the S, and same thing with the P. You have 2 electrons and 2s2, 6 and 2p, and therefore you have 8 electrons, octet. Now, there's one exception to the octet rule, and it's right here. Hydrogen's octet is 2. I'll say that again. In all the elements, the one exception to the octet rule is hydrogen. Its octet is 2. Now, when we talk about electrons in a molecule, there are two types. And the first type are called the bonded electrons. And those are pairs, remember pairs too, of valence electrons that are shared between atoms in a covalent bond. Again, bonded electrons are pairs of electrons that are shared between atoms in a covalent bond. Now, in certain molecules, certain atoms will have pairs of electrons that are not involved in chemical bond, and we call those non-bonding electrons. And those are pairs of valence electrons that are not involved in electron sharing, in other words, in a covalent bond. So you have bonded electrons. Those are pairs of electrons being shared in a covalent bond, and non-bonding electrons. Those are electrons not being pairs of electrons, not being shared in a chemical bond. Let's look at something more exciting than hydrogen. Oh, look, it's practicing Lewis structures for key molecules, otherwise known as Lewis structure practice time. And remember, practice makes perfect. Another way is saying that practice is good for your grade. Also, I'm being sneaky because if you practice it, you'll learn it. All right, let's get to work. Notice we have chlorine, water, and ammonia. Let's go to my whiteboard. Not named after me, just the color is, and color wasn't named after me. Uh-oh, not the whiteboard. Here we go. All right, so you're being asked to draw the Lewis structure for chlorine gas. Well, how do you do that? Well, first of all, I better open up my periodic table. All right, the first thing you have to do, and let me just do a double check. Thumbs up, people. You see the green periodic table. Thank you. All right, you have to find how many valence electrons chlorine has. Remember, valence electrons, the outermost electrons of an element. And you find that by looking at the Roman numeral, or in my case, what I've also given you, the numeric numeral, above the column that element sits in. Chlorine, a halogen, second to last column on the right, and it has 7 valence electrons. And that's not what I want. So we know chlorine has 7 valence electrons. Now, here's one chlorine. Remember, we do 1 dot on each side. And then here's another one. And this chlorine says to that one, I've got 1 unpaired electron. You've got 1 unpaired electron. Let's share. And they do. But the other electrons that were around each chlorine, valence electrons, are still there. Now, let's go to some colorful pens. This right here, those pairs of one pair are the bonded electrons. And these, including these, I'm not going to write boxes around all of them. Those are the non-bonded electrons. And you should be able to pick out bonded and non-bonded electrons. And there you go. Remember, covalent bond, sharing of pairs of electrons. And on a test, this is all you'd have to write, but these are things you have to consider. All right, let's try an important molecule in our daily life, water. Now, I'm going to let you try this one out first, and I'll do it. Hydrogen has one valence electron. Oxygen has 6 valence electrons. Now, in water, oxygen is in the center. Your turn. Draw the Lewis structure for water, 3 points each. And write the Lewis structure for each atom, and then see who can share a pair of single electrons with another single electron. All right, looks like everybody's done. I better get to work. Now, each hydrogen has one valence electron. Oxygen has 6 valence. And there are 2 hydrogens. And this hydrogen says to oxygen, I have a single electron, you have a single electron, let's share. And they do. And this electron on hydrogen says, I've got a single electron, you've got a single electron, oxygen, let's share. And they really do. And here we have the answer right here. That's the Lewis structure for water. Now, I would ask you, circle in water the bonded electrons. You do that first, then I'll do it. Give you 5 seconds. Go. 4.3, 4.4, 5. Time's up. And if we look here, here's a pair of electrons being shared, and here's a pair of electrons being shared, and these are the bonded electrons. Now, what are the other two pair of electrons in oxygen on oxygen called? And they're called the non-bonding electrons because they're not involved in a chemical bond. Oh, let's do another one. Ammonia, NH3, is a very important compound. And because chemists were able to finally, about 1910, figure out how to make that in a plant, that had two major effects on the world. One is once we could make cheap ammonia in a chemical plant, and that was by two German chemists, Haber and Bosch, came up with that. We now had a way of making cheap fertilizer. And now American farmers and everybody else, but it really helped American farmers then in the early 20th century, could make lots of food because they had lots of fertilizer. And that helped increase the population of our planet. Amazing, a little molecule of that. Now there's a dark side to that molecule. Ammonia, once you have it cheaply available, allows you to make explosives. And because there was now cheap ammonia, that made it possible for very bad and long wars, like World War I, World War II, the Korean War, and a whole lot of others. So there's good and bad. Hopefully by now you've written the Lewis structure, but oops, I didn't do something, sorry. Hydrogen has one valence electron, nitrogen 5. Now you can go ahead and do it. Oh my goodness, I think you guys are getting the hang of it. Doesn't that feel good? See, I told you chemistry isn't that hard. It's fun. All right, let's do it. Now, the only way you can make this work is to have nitrogen in the center. That's the Lewis structure with 5 valence electrons. Each hydrogen, there are 3 of them, has one, oops, let's make that part of the H, have one unpaired electron. This hydrogen says to nitrogen, let's share. And they do. And the bottom one says, let's share. And they do. And the last one also shares. And this would be the Lewis structure for ammonia, NH3. And I would ask you the following question. In ammonia, NH3, how many covalent bonds are there? And the answer is count pairs of shared electrons. 1, 2, 3. So there's 3 covalent bonds in ammonia. And if you notice in water, up here, there are 2 covalent bonds. So the next time you see a friend, loved one, or neighbor drinking water, you can say, you know that molecule of water you're drinking has 2 covalent bonds? People don't like to hear that when they're drinking water, trust me. All right, let's continue on. Now, it turns out with polyatomic ions, you have both ionic and covalent bonds in a molecule. And let's look at how we do that. This is NaOH, sodium hydroxide. The old name was lye. How many of you have heard of lye soap? This is used to make that. Now, first of all, let's look at the periodic table. Listen carefully, this is important. If you have a molecule with an alkali metal or an alkaline earth metal, first column or second column, excluding hydrogen, they will always be in an ionic bond. If you have lithium, sodium, potassium, magnesium, or calcium, they will never, ever be in a covalent bond. I've asked other chemists for years now, can you think of an example where I'm not right? and it is an ionic in a covalent bond? And the answer is no, they can't, because it doesn't exist. So remember, lithium, sodium, and potassium form a +1 cation. So let's look at the following. Draw the Lewis structure of sodium hydroxide. And that's a white solid at room temperature. Well, sodium has 1 valence electron, hydrogen has 1 valence electron, and oxygen has 6 valence electrons. And before we do this, Dr. White's been bad, shame on me. I forgot to point something out. Now, let me write water again down here. And if we look at around oxygen, both bonding and non-bonded electrons, how many do we have? 2, 4, 6, 8. The octet rule. Now, if we look at hydrogen, how many shared and non-shared or hydrogen doesn't have non-bonding. How many shared electrons, pairs of electrons does hydrogen have? And you notice that's 2. And remember, the octet rule for hydrogen is 2, not 8. And this hydrogen too has also 2. So everybody's happy. It's nice to have happy molecules. Now, if we look at ammonia, same thing. Let's just look at nitrogen and all the bonded and non-bonding electrons around nitrogen. How many? 2, 4, 6, 8. And it's got an octet. And if we look at either any one of the or all the hydrogens, it has 2 valence electrons. Remember, hydrogen has 2 valence electrons for its, or 2 electrons is its octet. Now, let's go back to sodium hydroxide. Now, sodium will form a +1 cation. It did. Oxygen has 6 valence electrons. Hydrogen has 1, says, oh, oxygen, I have 1, you have 1, let's share. Now, if you notice, sodium is happy because it gave up its electron and it's formed a stable cation. Hydrogen is happy because it has 2 electrons, it's octet. Uh-oh, look at the oxygen. There's only 7 electrons. That can't be right, but wait. Remember, sodium had 1 valence electron, but now it's missing that, it lost it. Where did it go? It went here to the oxygen. And now it has an extra electron and it has a negative charge, which hydroxide does. And now if we look at oxygen, it now has 8 valence electrons, it's happy. And that's the Lewis structure. Remember, all alkali metal and alkaline earth metals always form cations and are in an ionic bond. And sodium hydroxide, we have, ooh, I need some tea, excuse me. Test, cation, and all right, I'm working again. And in sodium hydroxide, we have 2 types of bonds. There's one ionic bond between the sodium and the hydroxide, and there's one covalent bond between the oxygen and the hydrogen. So there's 2 different types of bonds. And a lot of molecules in life, this exists. I'll talk more about it near about week 16 or 17 of the semester, which is down the road. But I hope you're all using soap. By the way, soap is very sophisticated organic chemistry. And whether you use bar soap or liquid soap, in your soap, there's both one ionic bond between sodium usually and other atom, and a lot of covalent bonds. So next time you use soap to wash your hands, notice I did, they're clean. And later in the semester, I'll teach you how soap actually gets stirred off your hands. That's going to be so exciting. You'll love it. But anyways, you have a lot of covalent bonds. So in soap, whether you have liquid or bar, you have both ionic and covalent bonds. Remember, chemistry is everywhere around you. I stole that from SpongeBob. Remember the one with imagination? The more complex the mind, the simpler the entertainment. I still love cartoons, even though they're not as good as when I was a kid. Now, who's the greatest chemist of all? Mother Nature. And if we just had one pair of electrons being shared, that'd be pretty boring. And we wouldn't have all the exciting things we have in our life, like our skin, what's left of my hair, my beard, my shirt, the dye in my shirt, all sorts of things. So what did Mother Nature do? She came up with a great thing and started organic chemist. What she did first, and that is multiple covalent bonds. When I was in college, I think I started in high school. I put a couple stars in the left margin. It's really important. If I put stars and the letters IMP with an arrow, I knew I better know that. All right, when it comes to covalent bonds, there are three types of bonds, and you should know. The first one is a single bond. And a single bond is a bond between which two atoms share one pair of electrons. Single bond, one pair of electron being shared. And next, if we go, we have a double bond. And a double bond involves a bond between two atoms, a bond in which two atoms share two pairs of electrons. Double bond, two pairs of electrons. So single bond, one pair of electron being shared, double bond, two pair. And we're not done. There's one more. And that is the triple bond. And a triple chemical, and these are all covalent bonds, a triple bond is a bond in which two atoms share three pairs of electrons. So triple bond, three pairs of electrons being shared. And an easier way of seeing that is this. Oh, hold on. I'll give you time for those who are writing. Triple bond, three pairs of electrons being shared. Single bond, one pair. Double bond, two pair. Triple bond, three pair. All right, come on. There we go. All right, and the first one is a single bond and one pair of electrons. Then we have a double bond, and that's two pair of electrons. And finally, we have a triple bond, and that's three pairs of electrons. All right, everybody together with Dr. White. What's the first type of covalent bond? Everybody, single bond. What's the second type? Double bond. What's the third type? Triple bond. You should remember, triple bond, one pair of electrons. Remember, pair means two. Double bond, two pair of electrons. Triple bond, three pair of electrons. So we have a single bond, one pair, double bond, two pair, triple bond, three pair. Now, if you know baseball, what happens when you get to first base? One, you have a single. What happens when you get to second base? Two, you have a double. And what happens when you get to third base? Three, you get a triple. So if you know your baseball, think about hits going to first, second, and third base, single, double, triple bond. Now let's practice one. Let's do nitrogen. And remember, there's now three types of covalent bonds, single, double, and triple. So draw the Lewis structure for nitrogen. I'll do this. Nitrogen has 5 valence electrons. When we're talking about bonding, we're only dealing with valence electrons. Now, each of nitrogen, if I draw the Lewis structure for the element, is this. And this nitrogen says to that one, oh, look, I have 1, 2, 3 single electrons. You have 1, 2, 3 single electrons. Let's share pairs of electrons, and they do. Now the non-bonding electrons come along for a ride. And notice each one had 3 electrons, so I have 3 pairs. And this is the Lewis structure for nitrogen gas. And what type of chemical bond, covalent chemical bond, is between nitrogen? 3 pair of electrons, that's a triple bond. And the next time you inhale, the nitrogen gas N2 in the air you're inhaling has a triple bond. So think about it this way. When you inhale, triple bonds are going into your lungs. If I look at the clock, we're just about out of time. Now, remember, first of all, if you haven't gotten your access code for Beyond Lab Z, come to my office hour tonight or late afternoon at 5, and we'll go through the lab together. And I'll help you generate the data, but you still have to write it. On Friday, I will go through chapter 3, practice problem set. Friday, chapter 3, practice problem set. I highly, highly recommend you do them before I do. Remember the story about the bicycle and falling off? Do you want to fall off on the test or the practice problems? Hope you all said practice problems. And with that, I'm out of time. Boy, time flies really quick when you're having fun with covalent bonds. With that, I'm going to say, gang gesund, goodbye. I stole that from Granny and the Beverly Hillbillies TV show. If you look on YouTube and you'll see it. Again, goodbye, gang.